I'm Giakkoupis, and I will talk about expanders via local edge flips in quasi-linear time. So we consider the flip process, which starts from an arbitrary connected irregular graph and applies a sequence of flip operations to it. A flip operation picks a random three-path A, B, C, D, and if edges A, C, and B, D do not exist already, then edges A, B, and C, D of the path are replaced by new edges AC and BD. Now, if any of these two edges exist already, then the operation does not modify the graph. Here's an example. Say this is the path that is picked, then these two edges are removed and they're replaced by these two new edges. Here's another example. Now, since edge BD exists already, the operation will not modify the graph. Note that flip operations maintain graph connectivity and they do not modify the degree of the vertices. The process was proposed by Malman and Sintelauer, who showed that the Markov chain that underlines the process converges to the uniform distribution over all connected irregular graphs. They also asked how long it takes before the graph is transformed into an expander graph. This and the related problem of bounding the mixing time of the Markov chain have been studied extensively ever since. Malman and Sintelauer also provided experimental evidence suggesting that order n d log n operation should suffice with high probability to obtain an expander. Some motivation: the flip process provides a very simple local Markov chain Monte Carlo process for sampling random connected irregular graphs. Because of its locality property, that is, each operation affects only a small number of adjacent vertices, the process is very easy to implement in parallel. Also, it provides a simple local process for generating and maintaining a deregular expander. Again, because of its locality property, is very suitable to the design of unstructured overlay networks. Such networks should typically have small diameter, low degree, and good connectivity, all of which are also properties of deregular expander graphs. We should note that edge flip-like operations are already customarily used in practice in overlay systems. A closely related process is the switch process, which uses switch operations instead of flip operation. A switch operation picks two edges A, B, and C, D at random. And then similarly to the flip operation, if edges A, C, and B, D do not exist, then edges A, B, and C, D are removed and replaced by edges A, C, and B, D. The process is known to converge to a random deregular graph. However, unlike the flip process, it is not local and it may disconnect the graph. As a result, it is not suitable for the design of overlay networks. There are also structure overlay designs for generating expander graphs via local transformations. A notable example is the skip plus graph algorithm. The algorithm is local and self-stabilizing and transforms any connected graph to one containing a spanning constant degree expander in order log square n synchronous rounds. However, the algorithm is complex, especially compared to the very simple flip process. As I've mentioned already, there is a lot of work on the flip process. Some of this work in their analysis use results for the flip process. So here I list the best known bounds for both processes. So it is known that both processes are rapidly mixing. However, the mixing time bounds that we know of are very large polynomials in n and d. The only exception is a very recent work by Tikhomirov and Youssef, who showed a bound of n log square n for the mixing time for any regular bipartite graph of constant degree. Better bounds are known for the time until an expander is obtained. Allen Zhu, Bhaskara, Latanzi, Mirokni, and Orikea have shown a sharp bound of ND for the switch processor and a bound of order n squared d squared for the flip processor. In this talk, we provide an improved result for this case here. So for the flip process and for the time until an expander is obtained with high probability. Our bound is of order ND polylog n. So here's the formal statement of the result for any n and any degree d, that is at least log square n. There exists a time t of order n d log square n such that applying t-flip operation to any connected irregular graph transform this graph into an expander with constant conductance with high probability. This is a significant improvement over the previous best result. In particular, result implies that the average number of operations per vertex is of order d log square n, which is polylogarithmic if d is polylogarithmic. Whereas the previous known bound implies that the average number of operations per vertex is quasi-linear in n. So a result that truly justifies the use of flip-like operations in practice. Also, our result is within polylogarithmic factors from similar bounds for the switch process, which is not local, and for the skip plus graph, which is more complex. And also our bound is within a single logarithmic factor of the optimal bound, and in fact, we believe that a refinement of our existing analysis could remove this extra logarithmic factor from the time bound and could also relax the constraint on d to logarithmic from log square. And finally, I should point out that the precise definition of the flip operation we use is slightly different than the original one, and it's the same as the one used by Allen Zhu et al. So recall that in the original definition, we pick a random three-path A, B, and C, D, whereas in the version that we consider, we first pick a random two-path A, B, C, and then if edge AC does not exist, then we choose the third edge CD in the path such that edge BD does not exist. As a result, our flip operation may have a higher success probability and may require a bit more rounds of communication to implement. Next, we give an overview of the analysis. The analysis consists of two parts. In the first part, we show that edge connectivity of at least d over half is achieved in order ND log square n operations, and that this edge connectivity is maintained for polynomial time thereafter. In the second part, we show that as long as the edge connectivity is at least d over half, constant conductance is achieved in order ND log n operations, and again, this is maintained for polynomial time thereafter. Note that in order to improve the overall time bound of the flip process to order ND log n, it suffices just to improve the first part of the analysis. The same is true if we want to relax the constraint on the degree from log square n to log n. In the edge connectivity analysis part, we first look at how the size of a single cut evolves over time. So consider such a cut S bar, and let C S be the size of a cut. So it's 4 in this example. Let also C prime of S be the cut size after a single flip operation. We observe that the size of a cut may change only in two different cases. The first case is when the three path of a flip operation looks like this. And in this case, the size of a cut increases by 2. The second case is when the path of a flip operation looks like that. And in this case, the size of a cut decreases by 2. We then have the following simple lower bound on the expectation of C prime of S. So this is the fraction of all edges in the graph that cross the cut. Note that this factor here is positive as long as the size of the cut is less than d. In particular, if it's less than 1 minus epsilon d, the formula becomes like this. It follows that the size of a cut behaves similarly to a biased random walk on the integers, as long as the size of a cut is at most 1 minus epsilon d. And then we have this lemma here. The lemma says that after order m times log n at most operation, the size of a cut becomes larger, namely at least 3d over 4. And moreover, as soon as it becomes larger, that is between d half and 3d over 4, it stays large thereafter, in the sense that it decreases by at most log n term in the next polynomial number of operations. So this lemma argues about a single cut. However, we would like to be able to argue about all cuts simultaneously in order to obtain a lower bound on the edge connectivity. Recall that the edge connectivity is the minimum cut size in the graph. Now, unfortunately, taking a union bound over all cuts does not work. The reason is that the probability of this lemma 1 is 1 minus 1 over poly n, and the total number of relevant cuts is larger than polynomial in n. So what we do, essentially, we deal with all sets of size between L and 2L only after dealing with sets of smaller size. Then we double the value of L and repeat the argument. So towards this goal, we prove the following result about the number of cuts. So let RLK be the set of all sets S of size at most L, for which the corresponding cut size is at most K. Then our lemma says that if for all sets S of size L, the corresponding cut size is greater than K, then there are at most n sets of size between L and 2L, for which the corresponding cut has size at most K. The proof is simple and use some argument on the sets S that are minimal elements of R12K. Okay, so now using this lemma 2 and the lemma 1 from the previous slide, which argues about a single cut, we're able to argue about multiple cuts simultaneously. This is just a restatement of the two lemmas for your convenience. And so what we do, we assume that the set RLK is empty throughout the process for some K in this range. And then using this lemma, we show that with high probability, the set R2L K prime becomes empty starting at time tau. And K prime is smaller than K by this logarithmic term. Then we repeat this argument for all values of L of this form between D and N. So we repeat the argument logarithmic number of times, and then combine these results to obtain that with high probability, this set becomes empty at this point. So this set being empty implies that the minimum cut size over all cuts is at least k double prime, which is this formula here. And so note that this lower bound on the minimum cut size is at least equal to the desired d over 2 bounds if we choose d, as long as d is large enough, at least log square n. And the time bound we obtain is t times log n over t, which is of order m log square n. So this completes the proof of the first part of the analysis. In the expansion analysis part, we will assume that the edge connectivity remains at least d over 2. For this part, it is no longer convenient to work directly with the cut size. And the reason is that the size of a cut may decrease in expectation, even though the expansion of the cut is small. Instead, we introduce a new parameter for a cut, which we call the strain of the cut. So let AVS denote the fraction of neighbors a vertex V has in set S. Then the strain of cut S bar, sigma of S, is the sum over all vertices V of the product AVS times AVS bar. Now, a simple and useful upper bound on the strain in terms of the cut size is this one. Sigma of S is greater or equal to twice the size of the cut over D. Note, however, that the value of the strain may be much smaller than this upper bound. And here are 3 examples. In the first 2, the value of the strain is close to the upper bound. In the third example, however, where we have a bipartite graph, the strain is 0, even though the cut size is the largest possible. Now, along the line of the analysis in the first part, we proceed to compute the expected change of the strain after a single flip operation. And the computations were a bit painful, but we obtain a relatively clean formula for the exact value. So the formula has a positive term and a negative term. Then the negative term turns out to be negligible for the setting we will apply the result, so we will ignore it. The positive term contains a sum over all edges UV of the square difference AUS minus AVS. Note that this difference is non-zero only if UV is a crossing edge or is adjacent to a crossing edge. And here are some examples of edges, color in green, in which the absolute difference is large, and thus they contribute a large value to the sum. By large, we mean at least some constant epsilon independent of the degree. And now in all these green edges, one endpoint has very many neighbors in S, and the other has very few. Okay, and now in order to apply this expectation result, we introduce the notion of an L-phi expander. So a deregular graph is an L-phi expander if for every cut S bar, we have that the size of S, the size of the cut is at least 5 times t times the minimum between L and the size of S. This implies that all sets of size at most L have conductance at least phi. And so we show that for any cut S bar in an L-phi expander where phi is a constant and such that the size of L is at least L and the cut strain is at least L over 4, the expected increase in the strain in a single operation is of order omega, the cut size over dm. Recall that this is similar to the expectation formula we had for the increase of the cut size in the first part. In fact, the only difference is this factor d in the denominator. For the proof, we use the formula from the previous slide. And note that in order to prove the lemma, it suffices to show that there are order C of S edges UV that contribute a constant term. So a constant term to this sum, similarly to the green edges that we saw in the previous slide. Very roughly, we distinguish two cases. In the first case, where the strain is relatively small compared to the cut size, it turns out that sufficiently many of the crossing edges look like those, so they're green edges. And so considering just the crossing edges in the cut suffices to prove the claim. We don't even to use the expansion property. For the case where the strain is larger, we do the following. We sort all vertices in increasing number of neighbors in S. So here we have 0 neighbors in S, 0, 1, 1, 2, 3, and so on. And then we argue that there is a vertical cut such that sufficiently many of the crossing edge of this new cut contribute a constant term to the sum. Okay, and and for the existence of this edge, we use that we use the expansion property. Now, using this lemma 3, we obtain a lemma for the strain that is similar to the lemma that we had for the cut size for a single cut in the first part. So this is a lemma we show for the strain. So assuming the graph remains L, phi expander for a conveniently chosen constant phi, then for every cut S bar, such that the size of S is at least L, each of the following statement holds with this large probability. So we have that after order at most M operations, the strain is large, at least L over 4. And also, as soon as the strain becomes larger, then it stays large, then it stays larger for a polynomial number of steps. And these two claims are analogous to those that we had in part 1. However, now we also need the third claim. So this claim C says that if the cut size is too large, so at least some constant gamma times LD, then even if its strain is small, the strain will become larger, at least L over 4, before the cut size becomes small. And we'll use this claim in order to bound the number of different cuts when we apply a union bound in the next slide to argue about multiple cuts simultaneously. And in fact, because of this last claim, we just need to take the union bound over all cuts for which the cut size becomes at most gamma times L times D at some point in the process. And using a well-known bound by target, we can we show that if the edge connectivity is C times mean, C mean, the number of sets is at most this n times twice the threshold over C mean times the Poilian factor. This Poilian factor is because we reapply targets bound after every flip operation. Now we use the assumption that the edge connectivity remains D over it. We substitute here, and we obtain that the number of sets is at least like that. And now because our lemma 4 holds with this large probability, as long as D is larger than, is at least of order log n, we apply a union bound. Okay, and the rest of the proof is straightforward. I just want to make one point. Our analysis of a single cut establishes lower bounds on the cut strain, but at some point we need to translate this lower bounds to lower bounds on the cut size. For that, we just use this simple relation we showed at the beginning between the cut, between the strain and the cut size. And I should now conclude. So we've shown that the local flip process translates any connected irregular graph with d over at least log square n to an expander after at most of the order d and d log square n operations with high probability. This result is tied within a logarithmic factor. We expect that this factor can be eliminated by a refinement of our approach, and that the same be true for relaxing the constraint on the degree from log square to log n. Proving similar bounds for sub-logarithmic degrees seems more challenging. In particular, the case of constant degree is an important open problem. Finally, it would be interesting to explore whether our results and techniques could be used to improve existing bounds on the mixing time of the process. Thank you.